I'm hoping that this video will be just in time for the Paper 3 Home A-Level practical paper or practical and synoptic paper next week. So I thought I would go through some of the practical skills and techniques that you will have picked up over the course of your A-Level studies and how you can use those and apply them to the questions that you're going to encounter in the paper. This is also, of course, very relevant for those who take Paper 3 or Paper 6 for IAL because the same sorts of questions come up in general. These are the specification references that mention specifically what I'm going to be going through today. So you need to demonstrate your knowledge of practical skills and techniques. So they are expecting that you have done a lot of practical work and that you can look at the work of other people and evaluate it. What is good about it, what is bad about it, what could be improved. And note both familiar and unfamiliar experiments. So in the home level paper 3, they very rarely directly ask you about the core practicals. There's usually a mention, a small question about it, but mostly it's a familiar looking experiment or it's something about the core practical work but just done in a slightly different way, and you need to be able to use your skills. The limitations of physical measurement. So this is the whole idea of uncertainties, accuracy, precision, all of this, and I'm going to be going through each of these one by one so that you can understand what they really mean when they say this. And then finally, you need to be able to use the correct terminology. They are very sticky about this. You cannot be loose about what you say. They have provided a glossary of terms that we're going to go through in a second, and they are expecting you to use those words. Okay, so let's have a look at that glossary. It's a whole bunch of them. I'm going to go through it one by one. It's not super exciting, but you genuinely do need to know these. So what is validity? If your measurement measures what it is supposed to be measuring, which sounds a bit silly, but if you do an experiment and you find your percentage error, which used to in the old days be called percentage difference. So you're looking at the percentage difference between the value you got and the true value. And you've also assessed your uncertainties as you've been going through this. Now, if your uncertainties are less than the percentage error, so with your uncertainties, you're saying, I'm sure that this is the correct answer with these bounds. If the actual value is outside of those bounds, in other words, the error is bigger than the uncertainty, then you did not measure what you were supposed to be measuring, and therefore your experiment is invalid. The next thing is this idea of the true value. It's the value that would have been obtained in an ideal measurement. And this is what they want you to say when they ask you about this. Or they give you somebody else's evaluation of their work, and they'll ask you to correct it. The true value is the ideal measurement. Accuracy and precision are very important ones. A measurement is accurate if it is judged to be close to the true value. Now note that it says accuracy cannot be quantified, because a lot of people believe that the percentage error gives you an idea of your accuracy. And in some ways it does. But when they say accuracy can't be quantified, they mean as you're doing the experiment, you can't say that you're being 100% accurate because there are too many variables. There are too many things that could go wrong as you're doing it, not even going wrong, random things that creep in, or systematic errors over which you have no control. So accuracy, how close you are to the true value, is going to be affected by both random and systematic errors, and I'll get back to those later on. What is precision? Now, this is the one that causes the most drama, because in the old days, resolution of the instrument was synonymous with precision. They used the resolution of the instrument. They called instruments more precise because they had a higher number of decimal places. That is not what precision is now, and they've actually tested this in the past because they know that students fundamentally mix those up. What precision actually is equality denoting the closeness of agreement between your repeat data. So for most experiments, it is appropriate to do a repeat set of data, 2 repeat sets of data for each value of your independent variable. And those 3 repeats should be very close together. You're measuring the same thing after all. Now, it would be very unusual if they were exactly the same, but they should be close together. That's showing that you have a high level of precision. It is only influenced by random effects, and we'll talk about that again in a second. And you can measure it with standard deviation, but at this level, you are not expected to. Okay, so let's look at accuracy and precision. We have 3 archers, and those archers are going to shoot their arrows, whatever those arrows are actually called, at these targets. Archer 1 shoots her arrows and they land there. Now clearly, Archer 1 is very skilled. But the problem is, the goal is to get them in the center of the yellow circle. So Archer 1 has a fundamental problem. Although she is very precise in that her repeat data clusters very closely together, she is not accurate because the true value is in the center of the yellow circle. Now, it's a small adjustment that she has to make, maybe to her stance or the way that she holds it, so that it just moves and she achieves that level of precision in the right place. So this is the idea of a systematic error. We know that accuracy is affected by both random and systematic errors. This is your accuracy being affected by a systematic error. Archer number 2 does this. Archer number 2 is also very good, but you can see that still not entirely accurate. Now these are random errors. They have pushed Archer number 2 off the true value, the center of the yellow, in different directions each time. But you'll note that if you were to calculate the mean of these values, then that would bring you to the center. So this is the power of the mean. It reduces the effect of random errors and brings your mean, providing you exclude anomalies, brings your value closer to the true value. Now this person is not very precise, because as you can see, they're getting a different, significantly different value each time. But the mean value will be very accurate. Of course, the goal is to be as precise as Archer number 1 and have all of your arrows land in the center of the yellow circle. If your archer, this archer here, you've got both random and potentially possibly systematic effects, and really you ought to be starting again. Okay, let's go back to our glossary terms. Repeatability and reproducibility. These have been asked before. Repeatability is a kind of precision. This is the precision that is gotten by a single operator using a single method over a short timescale. What this means is you repeat your experiment maybe the same day, maybe the next day, and you're getting results that are very close together. Or the other group in your class, the other students in your class are repeating the experiment using the same method, and they're getting very similar results. Reproducibility is a much bigger test of whether or not your measurement is valid. Because this is the precision, again, so we're looking at the values that are gotten from these experiments being very similar when you have different operators using different pieces of apparatus. So you're using a whole different way of, let's say, measuring G. And what you want to, in the end, is that the result of their G is very similar to the result of your G, even though they used a completely different method. So, like it says down here, this is a harder test of the quality of the data. Uncertainty is, like we say, our bounds within which we think we made an attempt to measure the true value of something, and we're saying, this is what I'm quoting as the true value, but I think that it's going to land somewhere in between these percentage borders. The interval within which the true value can be considered to lie with a given level of confidence. So that percentage that you give is your level of confidence. It's the instruments and the method used that cause this uncertainty, and we'll come back to calculating uncertainties later on in the video. The error, we've already referenced the percentage error, the difference between the measurement result and the true value. Our resolution. So this is what used to be called in the old days, the old specification, the precision of the instrument. It is the smallest measuring interval. So for example, on a meter rule, the resolution of a meter rule is 1 millimeter. And it is the source of uncertainty. So for single measurements, we usually say that the uncertainty is half the resolution. So again, for a meter rule, that would be plus or minus half a millimeter. And finally, your number of SF used. You have to be very careful with tables. So when it is measured data, raw data, you actually took a piece of equipment and you measured that object. All of the decimal places in that column in your table should match up because that instrument has a particular resolution. So with your meter rule, they all should be to the nearest millimeter. So even if you measure something that's, let's say, 12 centimeters long, you don't write down 12 on that table. You write down 12.0 because you measured it to the nearest millimeter. So all of your raw data, your measured data, should have all the decimal places to the correct number and all to the same number, unless for some reason you had to change instruments halfway through. So for example, with an ohm meter, you might have to change the range halfway through, and that would be reflected in the final measurements that you made. Calculated data, apart from a mean calculation, because a mean still comes from the measurements that you made, but calculated data should have the same number of SF as the smallest number in the raw data. And so when you have a calculated column, you've got to make sure that you match that SF to whatever you use to calculate it. The only exception to this is for natural logs or logs to base 10. Here they say use 2 or 3 decimal places. So the reason for that is if you don't use 2 or 3 decimal places, or if you try to match the significant figures, you might end up with a value that's the same for several of your readings. So just to separate the values out, 2 or 3 decimal places. Okay, let's talk about accuracy. A lot of the questions in the practical paper will say things like, how does this arrangement lead to more accurate values? Or how would you improve the accuracy of this method? Note again that it is influenced by random and systematic errors. So what your job is to look at either the description of the experiment that they give you, or particularly the diagram that they give you, because nothing on these papers is put there by accident. So you look at the diagram that they set up on the paper and you think to yourself, is this a decent way of doing this experiment based upon the experience that you've had? So you look at this and you say, what would cause either systematic errors or random errors, and then you make some attempt to fix it. You describe how you would fix it and what effect that would have. For example, the classic systematic error is a zero error check. So you check for it and you correct for it. Make sure you put down both of those things. Now, this works for pretty much anything. Every balance, every ammeter, every voltmeter, even a meter rule. If you're absolutely stuck, you can check for a zero error on a meter rule. The only thing it doesn't work for is ohm meters, because of course, when they're not connected, you're going to get an E or an infinity symbol, which is measuring the resistance of the air between the connections. So the only example is where you're not measuring from zero, but your first instinct should be looking at whatever instruments the people have used and have they done a zero error check. Number 2 is our first random error. Now, again, parallax errors are huge. Every time you measure against either a horizontal or a vertical meter rule, you've got to make sure that you are reading it at eye level. There are so many experiments that we do that involve a potential parallax error. So if there's a diagram that they've given you, draw in a little set square down at the bottom of the meter rule or over at the side, so that you're showing that you understand that that has got to be vertical and it's got to be horizontal. The other option is to use a pointer. So at the bottom of a spring, or where you are doing a stress-strain graph, for example, you can always have a little tag or a little pointer on it so that you line that up with your meter rule, and that is going to make your judgment more accurate because you are reducing your parallax error. Number 3, anything involving heat. Now be careful about this, because there are some experiments where it doesn't matter if there are heat losses. But if your experiment is going to be affected by heat loss, if your value that you're calculating is going to be more inaccurate because you're assuming that no heat is lost to the surroundings, then one of the biggest fixes is to ensure that there are none. So put insulation around it and put a lid on it. The other thing, in measuring temperature, especially of liquids or gases, if you're measuring temperature, then you've got to somehow stir the liquid or disperse the heat through the gas evenly. Because, of course, what you don't want is to be measuring the temperature of the liquid that's just around the bulb of the thermometer and not the liquid as a whole. So putting in a stirrer or mentioning in your answer to stir the liquid regularly or thoroughly throughout the experiment will add in this accuracy measure for you. Number 3, random, is reaction time. So again, we do a lot of experiments that involve timing. And reaction time, especially in things like oscillations, becomes a big source of uncertainty and a very difficult to measure source of uncertainty. So there are some ways to get around this. An anticipatory countdown. So you go 3, 2, 1, start. You are using a fiducial marker at the equilibrium position because that is where the pendulum or the trolley or the spring is moving fastest. And also because you can't have it at the extremes because, of course, the amplitude of your oscillation is going to decrease over time. So you need it at the center. Another idea is to start your timing after you've done one complete oscillation just to ensure you didn't add an extra force by pushing it. And so you know then that after one complete oscillation, it's in its true oscillation. And then finally, you can use light gates with a data logger depending on the oscillatory object or the object whose timing you're measuring. So just be careful with this one because a lot of students think this is sort of a fix-all. That, oh, I'll use a light gate with a data logger, that'll make it more accurate. And examiners are wise to this. And so they design experiments where you cannot realistically use a light gate with a data logger because you can't guarantee that the pendulum bob, for example, is going to break the light beam exactly where you want it to. So just be wary. It's certainly usable, but just make sure it's appropriate for the experiment. This goes for all of these, by the way. Yes, these are all great standard answers that you can use, but only if it's appropriate for the experiment. So you still have to use your experience. And also, going back to the light gate and data logger, remember to add the data logger. In the examiner's report from 2022, I think it was, the examiner was complaining that students were saying to use a light gate, but they hadn't added a data logger. And of course, the light gate doesn't do anything by itself. Random number 4 is take a mean. And again, this is a very standard answer, but you have to be very careful about what you say. Don't forget to say, repeat at each value of the independent variable, whatever that independent variable is, 3 times and take a mean. Because the repeating only allows you to judge your precision. The mean is what reduces the effect of the random error, like we saw with the archer and her target. Now, it doesn't reduce the random errors themselves. The random errors are still there. You're still off target slightly. But what the mean does is it smooths those out. But you cannot say smooths those out. He wants you to use the technical term. So this is the phrase, reduces the effect of random errors. And a best fit line, by the way, on your graph does the same thing. If you think about how you may have done repeats, you may have got a nice accurate mean, and then you put it on and you see that still it's not dead on the line. The best fit line reduces the effect of random errors again. Number 5, using a video. Where the time span is very short for your experiment, a video is wonderful, a nice high frame rate, 60 frames per second. You're going to be able to play it back and spot what happens. You do have to be very careful for objects that are falling through fluids, or if you're trying to measure G through a falling object. You have got to put that camera somewhere, which means at some point during the fall, unless it's a very, very short fall, you're going to have a parallax error from that camera. Now, don't forget that you've got to have the meter rule, for example, or whatever it is, the instrument that you're reading, that has got to be in the frame. The other great use of a video camera is for things where you have to measure 2 things simultaneously. So, for example, if you are tracking the potential difference across capacitor over time, it's incredibly difficult to spot your time and read the voltmeter at the same time. There are always going to be errors creeping in when you try and do that. So videoing the whole process and just watching it, stopping it and pausing it at each 10-second interval or whatever it is that you want is a great way of making sure that this timing error does not creep in. Another random error fix is doing multiple measurements at multiple orientations and taking a mean. So this is the classic how do you measure the diameter of a wire. For whatever experiment you might be using that wire for, Young modulus, or maybe you're doing some kind of resistance and resistivity experiment, and you need to find the cross-sectional area of the wire. This is a very old and gold method at this stage, and again in 2022, the principal examiner made a comment that most students seem to have figured this out now, the multiple orientations, 5 times down along the wire, etc., etc. So this is unlikely to reappear for a while, but you may be watching this video several years later, so it could be that it's disappeared in the last few years and it's ready for a comeback. Let's talk about uncertainty versus percentage uncertainty. What the uncertainty is, reminding ourselves of what the glossary said, it's the interval within which the true value can be considered to lie. And it is giving your level of confidence in your readings when you've considered all the instruments that you've used. The typical questions that come up with this is how could they reduce the uncertainty in their measurements, or how could they reduce the percentage uncertainty in their measurements? And be very careful and read that very carefully. Because if there's a percentage there, it's a whole host of different things that you have to do. So uncertainty is much more difficult to reduce. Percentage uncertainty is relatively easy to reduce. Please try not to say that reducing the uncertainty or the percentage uncertainty improves your accuracy, because it does not. Think of the example where you could have an enormous systematic error, and you're measuring away and you're finding your uncertainty and you're finding your percentage uncertainty, and you've got a nice low percentage uncertainty, let's say of 2%, and you're thinking to yourself, am I not brilliant? The problem is, if you didn't zero check your instrument at the start, or there's some other systematic error that has crept in, you are not going to see that in your measurements. And so you could be completely inaccurate and yet have a very small percentage uncertainty. So just be very careful. How do we reduce the U or the percentage U? Percentage uncertainty first. So the percentage uncertainty is the uncertainty in your instrument divided by the measurement that you made. That's one way of doing it for single measurements. So if you're just measuring one thing, you're measuring the length of a wire, and you're using a meter rule to do that, the resolution of a meter rule is 1 millimeter. Therefore, the uncertainty in a meter rule, when the measurement using a meter rule is 0.5 millimeters, you would then use that to calculate your percentage. So 0.5 millimeters over, let's call it 200 millimeters, times 100 is going to give you your percentage uncertainty in your length measurement. Now, how do we reduce the percentage uncertainty? Well, the first way to do it is to measure across multiple objects. So if you want to find the diameter of a coin, the diameter of a marble, the thickness of paper, the wavelength of a sound wave, you measure across 5, 6, 10, whatever is appropriate, depending on how small the object is. Stick two set squares on either end, line them up against a meter rule. Even better if you can line one end against the zero of the meter rule, and then measure across 10 coins and divide by 10. Because the percentage uncertainty increases the smaller the measurement you make with the same instrument. So I used the example of the length of the wire. 0.5 millimeters was our uncertainty, and we were measuring a wire of 200 millimeters. So you end up with quite a small percentage. But if you try and measure a wire of 2 centimeters, then you're going to end up with quite a large percentage. So the bigger you can make your measurement, the smaller your percentage uncertainty becomes. That's for percentage. The other option to reduce both your uncertainty and your percentage uncertainty is to use a higher resolution instrument, because the uncertainty in a measurement is half the resolution of the instrument. So that means that if you use a better instrument, then you are going to have a smaller uncertainty. And presumably, if you're measuring the same length at that point, or making the same measurement at that point, having a lower uncertainty will also reduce your percentage uncertainty. But you must remember that you have to pick an instrument that is appropriate for the measurement that you're making. So sometimes you have no choice in the resolution of the instrument. For example, a micrometer is a wonderful instrument and will measure between 0 and 25 millimeters with a resolution of 0.01 millimeters. So that means your uncertainty is 0.005 millimeters if you do a single measurement with that micrometer. The trouble is, if you're having to measure something that's longer than 25 millimeters, then you've got to go the next one up, which is the vernier calipers traditionally. Now, a vernier calipers will measure up to 15 centimeters, or 150 millimeters. I find it easier to think of all of them in millimeters. And then the resolution of the instrument moves by a factor of 10 each time. So this is up to 150 millimeters, and it's 0.1 millimeters. They are now accepting digital calipers. Digital calipers are the best of both worlds, because the digital calipers will measure to the 15 centimeters, but it gives you the same resolution as a micrometer of 0.01 millimeters. And then finally, anything above 15 centimeters, you have little choice but to use a meter rule with a resolution of 1 millimeter and an uncertainty of 0.5 millimeters. The uncertainties I've been talking about so far have been the uncertainties that go with the instruments that you're using. These are for single measurements. In reality, any scientist would not take a single measurement of any value if they could avoid it at all. So we try not to use the resolution of the instrument as our source of uncertainty if we can. The best way to do it is to take repeat measurements. Now, usually that will be of the dependent variable rather than the independent. The independent is probably a single measurement, at which point you will use the resolution of the instrument. The dependent variable should have repeats, and those repeats will probably show some variation. That variation may be less than the uncertainty of the instrument, at which point you have improved your uncertainty. But you can't be guaranteed of that. And to find the uncertainty in a set of repeat data, you use half the range of your repeats and then put that over the mean. Again, you might get an uncertainty that's lower than the instrument, or you might get an uncertainty that's higher. Either one is fine. You should not get an uncertainty of 0. If all of your repeats are exactly the same, then you have to default back to the uncertainty of your instrument at that point, half the resolution of the instrument. I hope this has been helpful. I hope you managed to see it before your Paper 3 exam, or Paper 6 if you're IAL. The best advice I can give you at this point is read everything on the paper, think about how you would do it based upon your practical experience, look at all the diagrams, add in set squares, drawing little eyes, think about parallax, think about zero errors, and just use what you have learned over the last 2 years while you've done your practical work to say something sensible on the paper.